push that rock here with some math. Let's discuss linear inequalities in two variables. Here we go. So let's give it some context. Let's say we run a small business that assembles hospital beds and wheelchairs for use in homes for people that have been put on hospice or home health care. And we have a few employees that take the parts and assemble them, these devices, and then we have one employee that tests them. And in a given week, we only have 240 labor hours available for assembly. So there's several workers, they're maybe some of them are full-time and some part-time or whatever, and whatever their number of hours, it's 240 or less. And then we have the one employee that tests them, and he's limited to 40 hours every week. And it takes 6 hours per hospital bed to assemble and a half an hour to test. And for each wheelchair, it takes 3 hours to assemble and an hour to test. And so we want to know maybe we're trying to meet a production, and we want to know how many hospital beds and wheelchairs we can assemble and test and have ready for delivery. And maybe we're trying to minimize the labor hours and maximize rental income for renting these devices, whatever. So we're going to look at this relationship. So here it is. We'll call beds the number of beds we rent or each week, or we put together and send out to the home health, X, and the number of wheelchairs, Y. And remember, to put together a bed, it's 6 hours per bed. And to put together wheelchairs, it's 3 hours per wheelchair. And that time added together has to be less than or equal to the available labor time, 240 hours. And for testing, we have a half an hour per bed plus an hour per wheelchair. And that has to be less than or equal to 40. And then, of course, we cannot have negative beds or negative wheelchairs. And so we could have 0 beds. We could just concentrate on wheelchairs in a given week. Maybe that's going to make us more money if we just put together and test wheelchairs and have them ready for home health use. So we could have 0 for both of these. So it's X is greater than or equal to 0 and Y is greater than or equal to 0 because it can't be negative. That means we're in quadrant 1 of the Cartesian plane. The Cartesian plane is a very nice visualization tool. So here's quadrant 1 of a Cartesian plane where we have the y-axis and the x-axis. And we'll look first at the inequality, 6x plus 3y is less than or equal to 240. And we say to graph this, let's just think of the line. Just think of the equality, 6x plus 3y equals 240. Well, that's easy to do. We subtract the 6x over, divide by 3, and we have a nice little line in mx plus b form. So the slope is -2. The y-intercept is 80. We know it intersects at 80. We know that if we go down 8 units, then we need to go over 4 units because 8 over 4 is 2. And so then we have a nice little line here. But it's an inequality. So the way you handle an inequality in this situation, you test some point on either side of the line. So I could come over here and test like 50, 20, which would be over here. But I'm going to test 10 over 10 of 10, 10, 10. And that's going to be real easy. I'm going to put it into the inequality, 10 for the x and 10 for the y. That gives me 6 times 10 is 60, and 3 times 10 is 30. That adds up to 90. That's clearly less than 240. So this is a true statement, which means that this point satisfies the inequality, which means it should be in the solution set. So that means instead of the points up here being solutions, the points down here are solutions. Now, some of you are thinking, oh, it was less than. It was less than, so of course I'm going to color down. Well, yes, if everything's positive, that's a nice little trick. But you got to be careful. If there's some negatives floating around, that little less than can mislead you, okay? If you got some negatives floating around in here, this less than might get you. So just test the point and make sure you're on the right side of the line and color that side. Now, I didn't color out here because remember we have to stay in quadrant 1. So we're trapped in quadrant 1, but we're below the line. Okay, let's look at the other constraint. We call these inequalities sometimes constraints in context of linear programming problems. That's another day, another topic for another day in another class probably. But here we go. We have 1/2 x plus y is less than or equal to 40. That was one of our inequalities in two variables. So we just look at the line. We make it equal. 1/2 x plus y equals 40. And we subtract that over. And now we know the y-intercept is 40 and the slope is down 1 over 2. So we got 40. Go down 1 and over 2, down 1 and over 2, and so forth till we land here. And we have the two intercepts. We draw the line. So, again, we test 10, 10. We put 10 in for x and 10 in for y, and we find out 15 is less than 40. So, yes, that's true. So, I should, again, color below. So, I color below the line instead of above. And, again, I stay trapped in quadrant 1. Now, what we were looking for was the solution set to both of these constraints, both constraints. Because if we come out here and pick a point out here, well, then we are outside the constraints, our labor constraints for assembly. We might have testing guy could handle 60 wheelchairs, I think with no beds, and 10 wheelchairs. He could handle it, but the assembly guys couldn't. So these points out here are not in the solution set. As of some of these points, the assembly guys can handle 10 beds and 70 wheelchairs or 60 wheelchairs, but they cannot. But the test guy wouldn't be able to handle it. So, what is the solution set that satisfies both of these inequalities? Well, all four of them. Well, it's in the first quadrant because of these two constraints. And then it has to be where it was red and green on the previous slide. So it's this little solution set here. We call this the solution region. It's all the points in this colored purple region that satisfy the four inequalities. And these vertices in a linear programming problem would become important. And this one we could find just by making these equal and solving that system of equations. That's something maybe important for a later date. I just want to teach you how to graph and represent solutions in the Cartesian plane, solutions to the linear inequalities, so to speak, two variable inequalities where there's no products or squares, just adding the variables, not multiplying them. So with this visualization tool, you will be able to do one of your tasks for this week. Math Made Simple. It's Simpson Math.